BYD's Super E platform delivers charging at a staggering 1,000 kilowatts, running on an 1,000-volt system, powerful enough to add 400 kilometers of range in just 5 minutes. For comparison, Tesla's superchargers are still operating at 400 volts. That simple numerical gap conceals the biggest technological battle unfolding in the EV industry right now. A battle that's no longer about who can drive farther, but about who can make you wait less. To understand this radical shift, we need to break down the physical wall that electric vehicles kept slamming into. For the past decade, the industry relied on a unified engineering template running at roughly 400 volts. That choice wasn't random. It was a purely economic decision. Power electronics components, transmission cables, and capacitors that operate at this voltage were widely available and cheap, largely because they were borrowed from other industrial applications. But as battery capacities ballooned to ease consumers' range anxiety, a fatal physical problem emerged: heat. According to the basic laws of electricity, boosting charging speed on a 400-volt system requires massively increasing the electrical current, the amperage, and that's exactly where the crisis lies. The higher the current, the more heat is generated inside the cables and connectors, and it grows exponentially. The traditional engineering fix for this was to thicken the copper cables so they could handle this violent surge of energy. The result? Extremely heavy cable bundles inside the car that add to its overall weight, reduce efficiency, and require charging cables at stations so thick that an average user struggles to bend or carry them. Not to mention the need to continuously pump coolant through the charging cable itself just to keep it from melting. The industry needed a genuine breakthrough, and that's where the race toward high-voltage architectures began. 800, 900, and even 1,000 volts. The golden rule here is simple. Doubling the voltage lets you transmit the same amount of power or even more using half the current. Less current means less heat. Less heat means thinner, lighter copper cables and simpler cooling. And ultimately, it means a lighter overall vehicle and charging speeds that were never possible before. But this transition isn't just a switch to flip or a software update. Raising the voltage to these levels requires re-engineering the car from the ground up. Older components made from standard silicon can't withstand this voltage and break down thermally. So companies were forced to shift to silicon carbide, SiC, in manufacturing their inverters. Silicon carbide is a superconductive material that handles enormous heat and frequencies with efficiency approaching 99%, cutting energy loss as direct current from the battery is converted into alternating current for the motors. This costly technical shift is now the filter, separating companies capable of leading the future from those that will get stuck in the past. The Germans grasped this reality quickly and moved with their full industrial weight. BMW rolled out its iX3 as the company's first fully 800-volt platform, capable of accepting charging speeds up to 400 kilowatts, enough to add up to 500 miles of range by European standards in record time. Mercedes wasn't standing idle either, launching the electric GLC with an 800-volt system and speeds of 330 kilowatts. Audi, meanwhile, decided to break through the psychological and technical barrier altogether by partnering with the Chinese giant CATL. The result is the luxury E7X, which doesn't stop at 800 volts, but pushes the architecture to 900 volts. This platform is backed by charging technology known as 4C. In battery terminology, the letter C refers to the charging rate relative to the battery's capacity. 4C technology means the ability to fully charge the battery 4 times within a single hour. In practical terms, this lets the E7X take its massive 109.3 kilowatt-hour battery from 10 to 80% in just 13 minutes. And add 429 kilometers of range in 10 minutes. We're talking about an energy flow rate that makes conventional chargers look like relics from the last century. Porsche, for its part, used high voltage to achieve a dual goal: fast charging and brutal performance. The new electric Cayenne, built on the 800-volt PPE platform, doesn't just fill its battery in 16 minutes, it also harnesses this high-energy transfer efficiency to generate 1,139 horsepower. That figure makes it the most powerful production car in Porsche's history, with acceleration that erases gravity, going from 0 to 97 kilometers per hour in 2.4 seconds. High voltage here ensures the motors don't melt while drawing this enormous power in fractions of a second. Korean manufacturers secured their seats in the front row early on. The Kia EV9 and Hyundai Ioniq 9 were built on 800-volt platforms from the start, delivering large family vehicles with ranges exceeding 620 kilometers and support for 350 kilowatt chargers. Even a storied performance brand like Maserati, with its Gran Turismo Folgore, adopted the same architecture to guarantee 100 kilometers of range added in under 5 minutes, because a Maserati driver simply doesn't have time to wait. Yet despite these achievements, a fierce chemical challenge is unfolding inside the battery cells themselves at these speeds. Pumping hundreds of kilowatts in all at once forces lithium ions to flow at tremendous speed from the positive electrode to the negative electrode. If that speed exceeds the electrode's ability to absorb it, a problem called lithium plating begins, where tiny needle-like metallic structures called dendrites start to form. These needles can pierce the battery's internal separator and cause a catastrophic electrical short. To avoid this, companies have developed extraordinarily complex thermal management systems that proactively cool the cells and control charging current down to the millisecond based on the temperature of each individual cell. But the bigger crisis doesn't lie inside the car, it lies outside it. Suppose a charging station has 10 cars parked, each drawing 1,000 kilowatts, that's 1 megawatt each. We're talking about pulling 10 megawatts from the local grid in a single instant. That load is equivalent to the consumption of an entire residential neighborhood or a massive steel plant. Electrical grids in most countries today simply aren't built to absorb a shock like that. And this is where the brilliance of the Chinese strategy comes into play. BYD isn't just building fast cars, it's building the entire ecosystem. The company's plan to roll out 6,000 flash charging stations across 312 Chinese cities doesn't rely on pulling power directly from the grid, which would risk collapsing it. Instead, the stations are integrated with massive energy storage systems, ESS. These central batteries at the station charge themselves slowly and continuously from the power grid or through solar panels. And when your car arrives, the station instantly unleashes its stored energy into your vehicle like a flood. This ingenious solution frees charging speed from the constraints of an aging power grid and turns 1,000 kilowatt charging into a tangible reality. This voltage race is redrawing the balance of power across the entire automotive industry. Superiority is no longer reserved for whoever offers a longer range, because consumers won't care about an extra 50 kilometers of range if a competitor offers charging 3 times faster. The equation has changed completely. And as we edge closer to solid-state battery technology capable of withstanding higher heat and faster currents without risk of meltdown, we're standing on the threshold of a historical moment. The moment electric vehicle charging actually becomes faster than filling a traditional fuel tank. So, the next time someone tells you an electric car takes too long to charge, remember, that argument is quickly becoming outdated. The real battle today isn't measured in kilometers of range, it's measured in minutes, seconds, even milliseconds of your time. From German engineering to Korean ambition to Chinese infrastructure, every major player in this industry has reached the same conclusion. The future doesn't belong to whoever builds the biggest battery, but to whoever makes you forget you're even waiting. And if this pace of innovation continues, we may be only a few years away from a moment nobody saw coming. The day plugging in your car becomes faster than filling it with gas ever was. If you found this breakdown valuable, make sure to subscribe for more deep dives into the technology reshaping the way we drive. Thanks for watching. I'll see you in the next one.